My dear students, welcome back to our channel. In this video, I will be explaining the BCA third semester subject Internet Protocols as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 3 first important short question is Routing Protocols. Routing protocols are the rules used by routers to find the best path to send data across a network. Just like Google Maps shows different routes to reach a destination, routing protocols help routers choose the fastest, shortest, or most efficient route for data packets. Why routing protocols are needed? The Internet is huge and has thousands of paths. Routers must decide which path is free, which route is shortest, which connection is working. Routing protocols provide this information. Types of routing protocols. 1. Distance vector, example, RIP. Chooses path based on distance, hops. Like choosing the route with the least number of signals. 2. Link state, example, OSPF. Routers share complete network information. Like seeing the entire city map before choosing the path. 3. Path vector, example, BGP. Used on the Internet between big networks. Like choosing routes between different cities. Example. If you send an email from Chennai to Mumbai, routers check routing protocols to decide the best path, maybe via Bengaluru or Hyderabad, depending on traffic. Easy trick to remember. Routing protocol is equal to Internet's GPS. Helps data reach the correct destination quickly and safely. Next important short question is 2. OSPF, Open Shortest Path First. OSPF is a popular routing protocol used inside large networks to find the shortest and best path for sending data. It uses the link state routing method, meaning each router has a complete map of the network. Think of OSPF like using Google Maps, which shows all roads and helps you choose the fastest route with real-time updates. How OSPF works? Simple explanation. 1. Each router shares its link information with all other routers. 2. Every router builds a network map. 3. Using Dijkstra's algorithm, OSPF calculates the shortest path. 4. Data is sent through the best possible route. Features of OSPF. Very fast at updating routes when network changes. Divides the network into areas, making it organized. Uses cost metric to choose routes. Lower cost is equal to better path. Example. If a link between two routers fails, OSPF quickly finds another route, just like Google Maps reroutes you when a road is blocked. Easy trick to remember. OSPF is equal to smart GPS for routers. It always finds the shortest, fastest, and most reliable path. Next important short question is 3. OSPF areas. In OSPF, Open Shortest Path First, a large network is divided into smaller parts called areas to make routing more organized and efficient. Think of it like dividing a big city into neighborhoods, so it's easier to manage traffic. Why OSPF areas are used? 1. Reduces routing overhead. Routers store information only about their own area. 2. Faster convergence. Changes in one area do not affect the entire network. 3. Simplifies management. Easier to troubleshoot and control large networks. Key points. Area 0, backbone area, the central area that connects all other areas. Non-backbone areas, connected to Area 0, can be standard or stub areas. Routers between areas are called area border routers, ABRs. Example. Imagine a company network with offices in Mumbai, Delhi, and Bengaluru. Each office is an OSPF area. Changes in Mumbai do not overload routers in Delhi or Bengaluru. All areas communicate through Area 0. Easy trick to remember. OSPF areas is equal to city neighborhoods. Each area manages its own traffic. The backbone, Area 0, is like main city roads connecting all neighborhoods. Using areas makes large networks faster, scalable, and easier to manage. Next important short question is 4. OSPF metric. In OSPF, open shortest path first, a metric is a number used to decide the best path for data to travel. The lower the metric, the better and faster the route. Think of it as choosing the quickest road on Google Maps. How OSPF metric works. OSPF calculates metric based on the cost of using a link. Cost is usually calculated as cost is equal to reference bandwidth link bandwidth. Higher bandwidth links have lower cost, so they are preferred. Example. Suppose a network has two paths from router A to router B. Path 1, 100 megabits per second cost is equal to 10. Path 2, 10 Mbps cost is equal to 100. OSPF will choose path 1 because it has a lower metric. Easy trick to remember. OSPF metric is equal to road traffic cost. Lower cost is equal to faster, smoother path. Higher cost is equal to slower or congested path. By using metrics, OSPF ensures that data always takes the most efficient route across the network. Next important short question is 5. BGP, Border Gateway Protocol. BGP is a routing protocol used to exchange routing information between large networks, autonomous systems, as on the Internet. Unlike OSPF, which works inside a single organization, BGP helps the Internet itself stay connected. Think of BGP as a postal service between cities. Each city, network, decides the best route to deliver letters to another city. How BGP works. BGP routers share paths to different networks instead of just distances. Uses path vector routing, which records the full path of autonomous systems a packet must travel. Helps prevent loops and ensures packets take a valid route. Example. A user in India wants to access a website hosted in the USA. BGP determines the best route between Indian ISP and US ISP networks, passing through intermediate networks if needed. Easy trick to remember. BGP is equal to Internet's travel guide. Shows all possible paths between networks. Chooses the best, loop-free path for data. BGP is crucial for the global Internet, keeping billions of devices connected efficiently across countries and networks. Next important short question is 6. BGP Path Vector Routing. Path vector routing is the method used by BGP, Border Gateway Protocol, to decide the best path between networks. Instead of just looking at distance, it keeps track of the entire path through all autonomous systems as to prevent routing loops. How it works. 1. Each BGP router maintains a path vector, which lists all as numbers a packet will pass through to reach a destination. 2. When a router advertises a route to its neighbor, it includes the full path. 3. Routers compare paths and choose the best route based on policies, path length, and reliability. Example. Suppose a packet travels from India, UK, USA, Canada. The path vector will record India, UK, USA, Canada. If another path through India, France, Canada is shorter or preferred, BGP selects it. Easy trick to remember. Path vector is equal to Internet's roadmap. Keeps a record of all stops. Ensures no loops. Helps BGP choose the most reliable and efficient route. Path vector routing makes BGP safe, loop-free, and suitable for the global Internet. Next important short question is 7. IPv6 Internet Protocol version 6. IPv6 is the latest version of the Internet Protocol used to identify devices and send data across networks. It was created because IPv4 addresses were running out due to the growing number of devices on the Internet. Key features of IPv6. 1. 128-bit address provides a huge number of addresses, tilde 340 undecillion, enough for every device on Earth. 2. Simpler header, faster processing in routers. 3. No need for NAT, each device can have a unique global address. 4. Built-in security, supports IPsec for secure communication. Example: IPv4 address 192.168.1.1. IPv6 address. Imagine IPv6 as new street addresses in a rapidly growing city where every house gets a unique number so no one gets lost. Easy trick to remember. IPv6 is equal to Internet 2.0 address system. More addresses, more devices connected. Faster, secure, and ready for the future Internet. IPv6 ensures the Internet can grow indefinitely without running out of addresses. Unit 3. Long questions. First important long question is 1. OSPF link state routing. OSPF, Open Shortest Path First, is a widely used interior routing protocol that operates using the link state routing method. Unlike distance vector protocols, like RIP, that only know the distance to a destination, link state routing gives routers a complete map of the network, allowing them to calculate the shortest and most efficient path for data. How link state routing works. 1. Neighbor discovery. Each router discovers its directly connected routers, neighbors, by sending hello packets. Example: Router A identifies router B and router C as neighbors. 2. Link state advertisement, LSA. Every router sends information about its connected links, link cost, and status to all routers in the area. Example: Router A tells others, I am connected to B with cost 10 and to C with cost 20. 3. Building the link state database, LSDB. All routers collect LSAs from others and create a complete network map. Each router now knows every router and link in the area. 4. Shortest path calculation. Routers use Dijkstra's algorithm to calculate the shortest path tree, SPT, from themselves to all destinations. Example: If sending data from router A to router D, OSPF chooses the path with the lowest total cost based on the network map. 5. Routing table update. The shortest path information is stored in the routing table, which is used to forward packets efficiently. Advantages of link state routing. Faster convergence, network changes propagate quickly. Scalable, can handle large networks using areas. Loop-free paths, complete network knowledge prevents routing loops. Flexible, supports multiple metrics, bandwidth, delay, cost. Real-life analogy. Imagine a city where each driver, router, knows all roads, distances, and traffic conditions. If a road closes, drivers immediately find a new fastest route. This is exactly how OSPF's link state routing works. Easy trick to remember. Link state is equal to complete network map. Every router knows the full map. Calculates shortest, fastest, and loop-free paths. Ensures efficient data delivery. OSPF link state routing makes networks fast, reliable, and smart, perfect for large enterprise and ISP networks. Next important long question is 2. OSPF types of links. In OSPF, open shortest path first. A link is a connection between a router and a network or another router. OSPF classifies links into different types to help calculate the best path using link state routing. Understanding these types is important for designing and managing OSPF networks. 1. Point-to-point link. Connects exactly to routers directly. Simple and fast, no need for special configuration. Example, two branch offices connected via a leased line. 2. Broadcast link. Connects multiple routers in a network, like Ethernet LAN. Routers can send messages to all devices using broadcast. Example, office LAN with 10 routers where all can communicate. 3. Non-broadcast multi-access, NBMA, link. Supports multiple routers, but does not allow broadcasts. Requires manual configuration of neighbors. Example, frame relay or ATM networks connecting multiple sites. 4. Point-to-multipoint link. A combination of point-to-point and broadcast. One router connects to multiple routers, but treats each as separate point-to-point links. Example, a router in headquarters connects individually to 3 branch routers over VPN. 5. Virtual link. Used to connect OSPF areas through a non-backbone area when direct connection to backbone, area 0, is missing. Ensures all areas can reach area 0. Example, area 2 is isolated. A virtual link through area 1 connects it to area 0. Easy trick to remember. Think of OSPF links as roads in a city. Point-to-point, single road between two houses. Broadcast, main street connecting many houses. NBMA, private roads, need directions to each house. Point-to-multipoint, one road splits into multiple smaller roads. Virtual link, temporary bridge connecting isolated areas. Understanding these link types helps OSPF calculate routes efficiently, reduce errors, and ensure fast convergence, making large networks reliable and manageable. Next important long question is 3. BGP path vector messages. BGP path vector messages. BGP, Border Gateway Protocol, uses path vector routing, and to exchange routing information, it sends path vector messages between routers. These messages help routers share network paths, prevent loops, and select the best route for internet traffic. Types of BGP messages. 1. Open message. Used to establish a connection between two BGP routers, peers. Contains information like as number, BGP version, and hold time. Example, router in India connects with a router in USA to exchange routing info. 2. Update message. Sends information about new paths, withdrawn routes, or path changes. Includes network prefix and as path, all as numbers the route passes through. Example, router announces, you can reach to 03.0.113.0/24 via as 100 as 200 as 300. 3. Keep alive message. Sent periodically to maintain the connection between BGP peers. Confirms that the neighbor is still alive and reachable. Example, every 60 seconds, router A tells router B, I am still here. 4. Notification message. Sent when there is an error or connection issue. contains the reason for termination of BGP session. Example, router detects a misconfiguration and sends a notification to terminate the session safely. How it works together. Open establish connection. Keep alive maintain connection. Update exchange routing information. Notification report errors. Real-life analogy. Think of BGP messages like letters between post offices. Open is equal to hello, let's talk. Update is equal to here are the new routes. Keep alive is equal to I am still here. Notification is equal to problem, fix needed. Easy trick to remember. BGP is equal to Internet's postal service. Each message has a specific role. Ensures reliable, loop-free, and efficient routing. Allows data to travel between countries and networks safely. BGP path vector messages make the global Internet stable, ensuring billions of users can access websites and services without interruption. Next important long question is 4. IPv6 addresses. IPv6 is the newest version of the Internet Protocol, designed to solve the problem of IPv4 address exhaustion. IPv6 uses 128-bit addresses, allowing an almost unlimited number of unique addresses for devices worldwide. Structure of IPv6 addresses. Written in hexadecimal, 0 to 9 and AF, and separated by colons. Example. Shortening rules. 1. Leading zeros in a block can be removed, 0370370. 2 consecutive blocks of zeros can be replaced by ones. Example. Types of IPv6 addresses. 1. Unicast. Represents a single device. Example, sending data from your laptop to a server. 2. Multicast. Represents a group of devices. Example, streaming a live webinar to multiple participants. 3. Anycast. Sent to the nearest device among a group. Example, requesting data from the closest content server. Advantages of IPv6 addresses. Supports huge number of devices globally. Simplifies network configuration with auto-configuration. Improves routing efficiency and security with built-in IPsec. Eliminates need for NAT, network address translation. Example in real life. Imagine India has billions of devices connecting to the Internet. IPv6 assigns unique addresses to every device, from laptops to IoT gadgets, without running out. Easy trick to remember. IPv6 is equal to Internet's mega address system. 128 bits almost unlimited addresses. Hexadecimal plus colons easy to write and shorten. Supports unicast, multicast, anycast. IPv6 ensures the Internet can grow forever, supporting billions of devices efficiently and securely. Next important long question is 5. IPv6 packet format. IPv6 is the newest Internet protocol, designed to handle the growing number of devices globally. Every data unit sent over a network is called a packet, and the IPv6 packet format shows how information is organized for delivery. Structure of an IPv6 packet. An IPv6 packet has two main parts. 1. IPv6 header, fixed size, 40 bytes. 2. Payload, data being sent, variable size. The IPv6 header is simpler than IPv4, which makes it faster to process in routers. IPv6 header fields, simple explanation. 1. Version, 4 bits identifies IPv6, value is equal to 6. 2. Traffic class, 8 bits indicates the priority of the packet, like urgent mail. 3. Flow label, 20 bits used for special routes for real-time traffic like video calls. 4. Payload length, 16 bits size of the data being carried. 5. Next header, 8 bits indicates the type of data or extension header. 6. Hop limit, 8 bits maximum number of routers a packet can pass, prevents infinite loops. 7. Source address, 128 bits address of the sender. 8. Destination address, 128 bits address of the receiver. Advantages of IPv6 packet format. Fixed header size, makes routing faster. Supports extension headers, adds extra features like security, fragmentation, or mobility without changing the main header. Efficient delivery, simplified structure reduces processing overhead in routers. Example. Sending a video from Mumbai to New York. Source address is equal to Mumbai device. Destination address is equal to New York server. Flow label is equal to real-time video. Hop limit is equal to 64. Payload is equal to video data. The IPv6 packet travels through multiple routers using this header information, ensuring it reaches the correct destination efficiently. Easy trick to remember. IPv6 packet is equal to simplified postal package. Header is equal to envelope with sender, receiver, priority, and instructions. Payload is equal to the content inside data. Extension headers is equal to optional notes for special handling. The IPv6 packet format makes the internet faster, scalable, and ready for billions of devices worldwide. Next important long question is 6. Comparison between IPv4 and IPv6 headers. IPv4 and IPv6 are versions of the Internet Protocol used to send data across networks, but their header formats differ significantly. Understanding this helps students know why IPv6 is faster and more efficient. 1. Header size. IPv4 20 to 60 bytes, variable size due to options. IPv6 fixed 40 bytes. Example, IPv6 is like a standard size envelope, while IPv4 can be bulky if extra options are added. 2. Address length. IPv4 32 bits about 4.3 billion addresses. IPv6 128 bits practically unlimited addresses. Example, IPv4 is like a city with a limited number of house numbers, while IPv6 gives unique addresses to every device on Earth. 3. Header complexity. IPv4 complex includes fields like checksum, fragmentation options. IPv6 simplified, many optional features moved to extension headers. Effect, IPv6 headers are faster to process in routers. 4. Fragmentation. IPv4 routers and sender can fragment packets. IPv6 only the sender fragments packets, routers forward them without fragmentation. Example, IPv6 is like sending a pre-sized package that fits all post offices limits. 5. Checksum. IPv4 has a header checksum field. IPv6 no checksum field, reliability handled by higher layers. Effect reduces processing time in IPv6. 6. Other differences. Feature IPv4 IPv6. Protocol version 4.6. Options in header extension headers. Security optional, IPsec, built-in IPsec. Mobility and QoS limited supported via flow label and extensions. Real-life analogy. IPv4 is equal to old postal system with limited addresses, bulky envelopes, and extra checks at every post office. IPv6 is equal to modern postal system with more addresses, standard envelope, and smarter delivery rules. Easy trick to remember. IPv4 is equal to old and limited. IPv6 is equal to fast and infinite. IPv6 solves address shortage, simplifies headers, and improves routing efficiency. This is why IPv6 is the future-ready protocol for the Internet, supporting billions of devices efficiently and securely.